difficulty to work with someone just because the reality is we learned this 2 days ago. Right? I don't expect us to fully master example problems literally 2 days after you learn. But good problems that we definitely want to be able to do. There are definitely different routes to take, so please ask questions if you tried something different. So the first one, you were given a domain, and you want to match it with a function that has that domain. So I just remember, okay, all my pre-calc knowledge is the same. If you have the ln of something, then that something has to be strictly greater than 0. If you have the square root of something, it has to be greater than or equal to 0. And if you have 1 over something, that denominator can't equal 0. So looking over here, my domain is a strictly less than inequality. So I know it's not going to be square root because it's greater than or equal to. And I know it's not going to be a fraction because the denominator can't be 0. So of course you could have found the domain of each of these and see which one matched up. But I'm going to take the road. I understand that if its y is less than 3 minus x, then it's going to be either b or e. So again, you could have found the domain of each of these, see which one matches up, or you can just kind of manipulate this to where everything is on one side of the inequality. So to get it to look like what answer choices over there look like. But then if I multiply everything by -1, now the direction of the inequality changes. That looks pretty good. So 3 minus x minus y is strictly greater than 0. That would be b. We all have 100% so far. Yeah.
So, are those the only functions that we're going to do, but we're going to get like sine and cosine?
Well, sine and cosine, the domain is only numbers. So we would have no issues there. There is one more thing that we need to be super careful of. Maybe we saw this in a pre-calc class. What if you have a square root in the denominator? Then true, because it's inside a square root, x minus 2 is to be strictly greater than or equal to 0, and then square root. However, because you're in the denominator, you can't have a value of 0. So this would actually change to y minus 2 is strictly greater than 0. So don't see this and always think like, oh, careful, it's always going to be ln. Not necessarily. Any questions on number 1? Of course, this could have been asked in the reverse direction. Maybe I gave you a function and then the answer choices are to match the domain. Number 2, 3 and 4 is everything we learned last time. This is just saying it now in words. Compute the rate of change at g at the point -2, 1 if x equals -2 and y varies. So y is the thing changing. We need to lock in that if y is the thing changing, you want the partial derivative with respect to y. X is fixed. So the goal here is to find the partial derivative with respect to y at the point -2, 1. There are 2 roads you could have taken. You could have said, well, taking this function, letting x be -2 and y varies, you can plug in -2 for x and keep y as y. That'll be 16y minus 5y plus 3. And then you could take the partial derivative with respect to y. That'll be 16 minus 10y. And then lastly, we got 6. That would have been answer choice C. I think this is kind of how I approached it the very first time that we saw this last time. But now that we understand that we can just take derivatives right off the bat, you don't have to plug in values. You could have just started by finding the partial derivative with respect to y and said that's 4x squared minus 10y, and then just evaluated that partial derivative at negative 2 comma. You're doing the same exact thing, we're maybe just changing the order. So that'll be 16 minus 10, you still get 6. So what I'm showing you here is really emphasizing we should be able to recognize the language of what the partial derivative is saying. If you travel in the y direction, but hold the other variable fixed, find the rate of change. It's just asking the partial derivative with respect to y. We all get number 2. Number 3 is simply just compute the partial derivative with respect to x. So the only thing that bothers me is this fraction here. Remembering that y is a constant, think of this as being like x over 1 plus 3, or like x over 4. If I wanted to take the derivative, I think we can all agree that that's going to be 1/4 of x. So if you wanted to just rewrite this in such a way that I can see what's happening as far as a constant, I'm going to call this 1 over 1 plus y times x. So it's written as a constant times x. So now my partial derivative with respect to x, you can't write z prime anymore. You have to show what variable you're taking the derivative with respect to. That'll be negative sine of keep the inside the same times derivative of the inside with respect to x, so times 2x. Plus, my constant stays the same. And I think the answer choice had this as negative 2x. Which that's looking like answer choice C. Last one. Given some sort of function, this is just making sure that we understand notation. Evaluate h of 1 comma 0 plus the partial derivative at 1 comma 0. So you're just evaluating the function, finding the partial derivative, adding them together. So h of 1 comma 0, that's 4 times 1 minus 6 times 1 times 0 plus e to the 1 times 0. 4 times 1 is 4 minus 0. Yep, don't forget e to the 0 is 1. So we get h of 1 comma 0 is 5. That's just this first piece. Now I'm going to compute my partial derivative with respect to x, and then plug in 1 comma 0. Partial derivative with respect to x, that's 4 minus 6y plus, this is the only tricky piece, if this is e to the xy, that's kind of like saying e to the 6x. And I agree that the derivative there is 6 e to the 6x. So my derivative should be y e to the 6xy. now plugging in 1, 0, which this chain rule piece was super important because now 0 times anything drops off.
Son of a gun. Damn. Got us. Oh, didn't you add them? Oh, man. You didn't say that. You did say that. Wow.
All right. If we miss 4, what do we miss?
Just the E times.
Yeah, that Y becomes 0. Yeah. And then we didn't add them together anyway, so. Yeah, we flaked on that one. That's all right. We did well. That was a tricky one.
All right, content-wise, I think I made a promise that you guys are gonna like this. It feels more familiar, right? It feels like stuff we've seen before. It's just like a natural extension of extending this to 3. So keeping exactly in line with that, we're now going to talk about tangent planes. So of course, we're going to review some calculus. So in Calc 1, one of the things we were often asked to do was to write an equation of a tangent line. And there was always different information running around, maybe a formula, maybe a table. Here we were just given values for f and f prime. So just like I would show in my Calc 1 class, if we want to write the equation of a line, we need a point. Slope. F of 2, 3 is showing the point 2, 3. That is a coordinate. And f prime of 2 equals -4. The derivative is the slope of the tangent line. So the slope of the line is -4. Don't think of it as a coordinate, 2, -4. That's just saying the slope of that line is -4. So then we go to our handy-dandy y minus y1 equals m times x minus x1. So y minus the y coordinate equals the slope, or m, times x minus the x coordinate. Last thing I'm going to do is just clean this up, do some quick math. So now the part B for these kinds of questions that we always had in Calc 1, is we wanted to use that tangent line. And we realized that these tangent lines have properties of quote-unquote local linearity, which says if you were to zoom into that point where the line touches the function, then it starts becoming a little hazy, the difference between what is the line and what is the original curve. So we stumbled on this idea that a tangent line is a really good approximation for the function around that x coordinate. So part B, we were asked questions like, use your tangent line to approximate values nearby. So I can say use it to approximate f of 2.2. And now this is the line that we need to really be able to make sense of. We can say our function behaves like that line near x equals 2. That's just something that we need to let sink in, especially for our Calc 3 lesson that we're about to see. I have no idea what the function f looks like. I only know that when you go to 2, you have a y-coordinate of 3. And when you go to 2, that the function is decreasing, because my derivative is, that's all I know. But I can approximate values in that neighborhood by using this tangent line. So I can say f of 2.2 is going to be roughly negative 4 times 2.2 plus 11. And someone with a calculator, what does that work out? What is it?
38 plus 11, negative 77.
Yeah.
72.
Negative 2.2?
Oh man.
2.2.
Oh, yeah.
Is it really 2.2?
It's just
Yes,
2.2.
Oh, it's a coincidence, I promise, that the x and the y are the same. It's just a coincidence.
Oh yeah.
So this is what we did in Calc 1. We were given some information. We can create a tangent line. And then we said that in that neighborhood, that line can be a really good approximation for the curve. So we're just going to extend this to Calc 3. Given some sort of surface, you can create a tangent plane. It turns out that in that neighborhood, that plane will be a pretty good approximation of values of the surface nearby. So let's go ahead and look at our tangent plane. So if I want a tangent plane at the point A, comma B, don't forget, values of the domain, values of the input are now ordered pairs. You need an x and a y. So like over here, it was write an equation of the tangent line at x equals 2. Now you need both an x and a y. Let's call this A and B. So that means the point on the surface is going to be x comma y comma z, where x is A, y is B, makes sense so far, and then the z coordinate, that kind of makes sense. It's whatever you get when you plug A and B into your original function. Then this kind of looks like our original point-slope form from Calc 1. Your equation of a tangent plane is going to be z minus, don't forget, this is really just saying the z coordinate. So z minus the z coordinate is equal to the slope times x minus the x coordinate, but in Calc 3, it's the slope in the x direction at a comma b. So the partial derivative at that. Say it. And then, oh, I guess.
Yeah, okay. Let's have a look.
To keep up with the notation, we should say that. Now there's just a slight extension to it. Plus the partial derivative in the y direction times y minus the y coordinate. So again, it feels really familiar. So then having this look just like our Calc 1 problem, you were given f of 2 equals 3, f prime of 2 is negative 4. The Calc 3 equivalent of that is given some information about this function. Just making sense of it for a second. This is saying when you go to the point 2, 3 in the xy plane, you're going to go up 2 units. So this is representing the point 2, 3, 2. This is saying standing at the point 2, 3 on top of your surface, if you travel in the positive x direction towards the big X in Desmos, you're going to be walking downhill. Your z is decreasing. Standing at that same point, if you turn 90 degrees and travel towards the positive y-axis, you're going to be walking uphill. So then the equation of the tangent plane is going to be z minus the z coordinate equals the partial derivative with respect to x times x minus the x coordinate plus the partial derivative with respect to y times y minus the y. Now, this is the tangent plane. If you graph this in Desmos, you're going to get a plane. But there are two different ways that you could write it. It could ask it in standard form, which is often how we were writing it on exam 2. that's kind of the exam one way that we were writing. That's our standard form. The reason we were writing it like that is you can easily identify the normal vector. So you could easily extract the normal vectors to be 1, -5, 1. That's why we wrote that in example. In exam 2, it wouldn't be crazy to try to write this as z equals something. So if you wanted to solve for z, you could say z equals 5y minus x minus 11. So exam 2, we're shifting to talking about functions. So writing this as z equals something is equivalent to the calc 1 way of writing it as y equals something. So you can make the same analogy here. Sometimes in calc 1 it wanted it in point slip. Sometimes it wanted it as y equals something. The reason that we're always going to do this is so you can make that same leap in calc 3 and say, that means this surface, that I have no idea what it looks like, behaves like this function, 5y minus x minus 11. So it's really just kind of, pay attention to what the question is looking for. You're going to write a plane. If it wants it in standard form, sure. If it asks for the normal vector to the plane, that's perfect. Then you would write it in this form so you can get a normal. But if we're going to see a part B, like I'll write in just a second, where we want to approximate values nearby, then I want to write it as z equals something, so I can say, that means this surface behaves like this plane, but we want to add this extension on here, near the point 2, 3. So then the part B feels almost identical. Use your tangent plane to approximate a value nearby. So instead of approximating things, or instead of plugging in 2, 3, you can plug in something awfully close, like the point 2.1, 2.0. So I can just drop it in over here. That means f of 2.1, 2.9 is going to be roughly 5 times the y coordinate minus the x coordinate minus 11. Something with a calculator.
1.4.
So go ahead and take Desmos out if you don't have it already. Write an equation of the plane tangent at the point 0, 1, and then just verify your answer in Desmos. And we'll be able to see visually, if you have some sort of surface, what the tangent plane would look like. Here we have a function, and the first example, we were just given the values. Now you might have to actually do some work and compute them. Find the partial derivative with respect to x. Then plug in 0, 1. Find the partial derivative with respect to y. Plug in 0, 1.
4. You should have that +4, maybe. I don't think.
Oh, hang on.
Yeah, that +4 needs to go away. Okay. Okay, there you go.
Alright, it's almost like that's why part B is check your answer.
Right. It's like, yeah, lay down. Lay down. Tired. Up late doing this work, and I have to get that girl needs to come back in here. Oh, it's paying off, I think.
Alright. So I grabbed my function. So I've got the point 0, 1, 6. I've got my tangent plane here. Graphing in Desmos, that looks pretty good. That is a plane tangent to the surface.
Wow, yeah. Point.
We wanted to maybe just shrink the window just so we can be a little more condensed here. Sometimes the plane is so steep it's hard to tell, but if you change the window a bit, you can see exactly, oh, there it is. That's a tangent.
Wow.
All right, so I've got two things coming around. I've got practice problems for you guys to practice, solutions online. The next thing is a Desmos project. It's super short. It's just really making sure that the A know how to use Desmos. B, create a tangent point. The only thing I will have to show you one more thing for the project. Say I want to be able to compute the partial derivative in Desmos. You can do that, but it would take one quick line before you do that. Desmos on its own does not know what f sub x means. So you're just going to spend one line in Desmos where you just define that to be the derivative with respect to x of your function. Now go ahead and just turn that off. It's going to plot something, just turn it off. Now you can tell Desmos what is the partial derivative at 3, 4, and it will compute it. So again, it doesn't know partial derivatives by default. You're just going to have to take 2 seconds, have one line where you just define it. How many more do I need? Who did not get a project? So
2, I think. Sweet.
says at the point, -1, -2, -18. Yeah, it should be 26 should be the Z coordinate. That won't change the derivatives or anything. Just change the problem. Change the -18 to the, it should be 26. So the problem line says, the problem says that the Z coordinate is -18, but if you plug in -1 and -2, you would actually get 26. It won't happen. All right, just for the last couple minutes, while I'll be here kind of standing over your shoulder, try to take a stab at the Desmos project. I think something like that, having someone looking over your shoulder. It'll be Desmos 3D. I'm just showing you, this is what I made my Calc 1 students do the other day.
Oh, wow.
So in Calc 1 the other day, I made them do this. They wrote a Desmos sheet where they can use a slider and draw the tangent line at any x value. You guys are going to do the same exact thing in Desmos, but have Desmos then output the tangent plane at any point. So you should be able to drag that point around, and it will always draw the tangent plane to the surface. And it should be dynamic. So what I mean by that is I should be able to go up to my original function and then change this to anything, and it still sketches the tangent. So don't just come up with an example and then compute derivatives. Like I should be able to come up behind you and change the function, and still it's going to draw the tangent plane. want this thing to be a function, and it turns out that's not a function.
Oh, okay.
If you have this, if you delete the square, and just
Well, you mean up here?
yeah, if you just make it z equals, then it's a function. Now do something where the y is actually. Not saying just do make it cosine x cosine.
Oh, yeah,
That's
yeah.
what I know. Two.
Oh, okay.
Now so. Just do it blindly. Also, do x equals also. Don't refresh it. Okay, there we go. And then you can like limit yourself by going to settings and shrink the z value. So like just the z value.
Oh, wow, that's kind of cool. Like that.
Click out of it, let's see how it looks. So that would only work for 2. So for 3D, we want our tangent plane, which is completely better. The tangent plane.
Can I use Z as a
You're good.
function?
What?
Alright,
Partials
we-
defined as So have a surface, have f of x comma y equals. That's just something you can look at. Now how growth through partials. Alright, so that is a project. It's not due right now or anything. You have until the next exams to email it to me. But when you do have it, email me or email it to me. And I will see everyone on Monday.
This is project what? Project 2? Or no, not 2. Come on, we did like 4 maybe.
I
Yeah,
think this is like
4.
Thank you for your help.
Okay. Let's go.